All right, welcome back. So what I'd like to do this time is a little bit different from what I've done before with the videos, in that today I just want to review and give you a chance to try out, can you get these correct? Finding derivatives of a variety of functions. So you can see right here, we've got 1, 2, 3, 4, 5 different functions. I'm just calling them all c of x for right now, and on the right we're going to try to write out the function that is the derivative of c of x, also known as c prime of x, or r sub capital C of x. In any case, all of these use chain rule at some point in time. So what I would suggest, if you're watching this video, pause where you can see all of these on your screen. Maybe grab a copy of your derivative rules from Canvas, maybe print it out, or if you have a file open, you can just flip back and forth like I did now and see what you can do with these questions and try them out and then restart the video. I'm just going to go ahead and write out the solutions to these right now. So in the first case here, c of x, I've got a cosine of natural log of x. So thinking about our chain rule, let me get my writing thing restarted here. Thinking about chain rule, I have an inner function that's natural log of x. Its derivative is 1 over x, or 1 over x times natural log of e. And then I'm going to multiply this chain rule factor onto the derivative of the outer function with respect to the inner, meaning the derivative of a cosine function is a negative sine function. Derivative of cosine of x is just negative sine of x. Derivative of cosine of this is going to be negative sine of the exact same thing, natural log of x, with this extra factor tagged on, the derivative of the inside. So the derivative of this first c of x is 1 over x times negative sine of natural log of x. Let's look at the second one. Sine of x is the inner function to a logarithm this time. So I've got, the first one was inner is a logarithm, outer is a trig function. This is the reverse. So just thinking about this in the same order, I'll swap colors so it doesn't get confusing. Inner function sine of x, derivative is cosine of x. And I want to multiply cosine of x, this extra chain rule factor, onto the derivative of log base 5 of sine of x. So thinking about log base 5 of something else. So log base 5 of x would be 1 over x times the natural log of 5. Log base 5 of something else is 1 over that something else times natural log of 5. I'm just going to write ln this way so it doesn't look like I have a 1 or something. So again, the rule is I've got my, if I think of each of these as g of f of x, so I'm naming the inner function f and the outer function g. This is f prime of x. This is g prime, but with f of x, the original inner function, still intact in the inside. So I still have, instead of 1 over x, I have 1 over f of x, 1 over sine of x. That's a part of this. And by the way, this natural log of 5 is in the denominator there. All right, so third question. I've got an inner function that has 2 terms. So it's a 2-term expression that's squared. This one you could multiply out if you wanted to, expand the binomial or whatever. It's not quite a binomial. I've got a radical expression, not a whole number power. But I could expand this if I want, or in terms of chain rule, the derivative of the inside part is 1 over 2 square root of x plus the derivative of e cubed. Make sure you're careful with that. Notice it does not have an x. We're doing derivatives with respect to x. This is a constant. So its derivative is 0. So I'd have a plus 0 as the derivative of the inside function. And then outer function, I've got squared. Derivative of x squared is 2x to the first. Derivative of this thing squared is 2 times this thing, 2 times f of x to the first. And this would be algebraically equivalent to what you'd get if you squared this out, like root x plus e cubed times root x plus e cubed. It would come out to be the same thing, and then it would simplify quite a bit, because square root of x squared makes x, assuming that square root of x is well defined, meaning x is greater than or equal to 0. But here we go. Now our next function here doesn't look too complex, but again, keep in mind we did one like this last time. The 6 and the 7 you can't make into a 42 because this is 6 to the first power and 7 to a different power, so they're not 42 of anything. It's just two separate terms, or it's a constant coefficient of 6. So when I write out my derivative with respect to x, I'm just going to copy down that constant coefficient, or that constant multiple that scales up the value of the derivative by a factor of 6, or scales up this rate of change. Now the derivative of 7 to the x power would just be 7 to the x times natural log of 7. This time I've got not just an x, I've got a tangent of x, whose derivative is secant squared of x. So here's my chain rule factor. And then the derivative of the outer function, which was exponential. 7 to the x would be 7 to the x natural log of 7. 7 to the something else is still 7 to that something else. That's an x in there, times the natural log of 7. So the 6 coefficient is multiplied onto all of that. This is 1, 2, 3, 4 factors all multiplied together. There's no distributing since there's no addition or subtraction. All right, now, just note, this last one looks awful, but in large part, it's combinations of things we already did. Notice the first term is exactly what we did here, and the second term under the subtraction is the very first question we just did. So if I want to find the derivative of this lovely thing, it's going to involve a couple different rounds of chain rule. So if I think about, well, how do I find the derivative of the inside function? It's all this stuff under the radical sign, which we worked out in advance. Each of those involves chain rule, but, well, I know this part is the derivative of the first term. So I'm going to start my derivative over here. C prime of x. The chain rule factor is going to be, from the first term, 6 secant squared of x times 7 to the tangent of x power times the natural log of 7 minus cosine of natural log of x's derivative. So this is the derivative of what's under the radical sign. We have that right here, minus then 1 over x times negative sign. I'm going to make this a plus, and then just leave the negative out of the middle of the multiplication. Oops, not secant. Sine of natural log of x. So this is just copying down the derivative of this and the derivative of that we worked out earlier and subtracting them. But subtracting this one that's negative turns into a plus. And then all we've got is the derivative of a square root function left to take. Square root of x's derivative is 1 over 2 root x. Square root of this is going to be 1 over 2 times the square root of, well, same thing as the square root of last time. 6 times 7 to the tangent of x minus, apologize for the x doesn't want to write, minus cosine natural log of x. And that's all under a square root in the denominator along with that too. And that's that. So this awful looking fifth problem here, if you work out the pieces of it individually, and this is a tactic I'll advise for long looking problems, work out derivatives of the various pieces of long looking expressions separately so that you can focus on the overall structure. So overall I've got a square root function, but underneath I've got two terms. Each of those two terms I can find the derivative of, which I'd need to for chain rule, this composition of function structure. But each of these also involves chain rule. So sometimes I think it's easier to start from the outside and work in, sometimes start from the inside and work out. But that's those questions. I have several more for you. I'm going to clear this off and move on to a next page of questions where I'm going to ask you again to take a look, pause, and see if you can try them. All right. Oops. Get this. There we go. So I called this a mastery self-quiz. So these first 5 are pretty short. Your mastery test has 2 halves to it, or 2 parts to it, I should say. They are worth the same number of points. They're not the same number of questions long. What you're going to see on the actual mastery test is that you're going to have 25 questions. They're about the difficulty level of this. They're worth 2 points each in terms of the 100 points on the test. And they're about this difficulty level. They're basically things straight off of the derivative rules sheet, nothing too fancy. Y equals secant of x, y equals log base 2 of x, y equals pi to the x, y equals arc cosine. There's only so many different variations we can have. The most challenging thing you might see on there is maybe a coefficient in addition to the rules you normally see, or just power rule expressions not written in power function form. There will be 10 other questions that are worth 5 points each. And those other 10 questions are not this difficulty level. They range from medium to pretty challenging. Medium might be just a simple example of power, or like product rule, x squared times natural log of x, or a simple quotient rule, cosine of x divided by 2 to the x, something simple like that. The more challenging ones, like the one that we just went through. So in any case, pause for a moment. Here's first 5 questions. I hope these take you maybe a minute or 2 to remember how to do the derivatives of each of these 5. And I'll be back with answers when you restart your video. So I'm restarting now. If I want to find the derivative of secant of x, make sure you name your function. Don't just write the function rule part. So I'll call it y prime. Derivative of secant of x is secant of x, tangent of x. Sometimes you'll see parentheses around those arguments, sometimes not, if they're just single terms like this. I'm not going to write them right now because my pen's acting up and it keeps putting extra lines and stuff. Y equals log base 2 of x. I could call it y prime. Well, let me just use a different notation here. I'll use dy over dx, the derivative of y with respect to x, that ratio of changes for a log function. That's a 1 over sort of construction, a reciprocal structure. 1 over x times a natural log of 2. It's always a natural log of a number, not a natural log of x, that shows up in the derivative of these. For y equals pi to the x power. So let me do this. R sub y of x. I'll call it that. Rate of change of y with respect to x. Now, make sure you're careful with these types of expressions. This is a number raised to a variable power. That makes it an exponential expression, like 2 to the x, e to the x, not a power function. So you're not going to be subtracting anything from the exponent, just like e to the x, pi to the x, which is just a little bit more than 3 to the x, is part of its own derivative. Then we just have times the natural log of the base. So derivative of pi to the x is pi to the x times the natural log of pi. Arc cosine of x. Well, it's not a very pleasant function, but arc cosine of x, if you memorize your rules, derivative of this is a fraction, has a negative sign in it, as does arc cosecant and arc cotangent. The denominator here is the square root of 1 minus x squared. So thinking about this, if you want to make some sense of cosines and sines and arc cosines and arc sines, if you remember sine functions and cosine functions, the domain is all real numbers, but the range of them, the output from a sine or a cosine function, unless you throw on a coefficient, is just going to be between -1 and 1. So when you're looking at inverse cosine and sine functions, so arc cosine or arc sine, that's the domain of those. So the domain is going to be between 1 and -1. And in the case of these, so that the due to the periodicity of it, we don't want them to violate function rules. We don't include 1 and -1. Also, in terms of looking at this, you can see, oh, the derivative wouldn't be defined at 1 and -1, but it does exist as a part of the function. So -1 through 1 is the domain of arcsine and arc cosine, meaning those are the numbers you're going to put into the functions, and you get out those different angles. So in any case, then you can see that, oh yeah, 1 to -1 are the sorts of numbers that would make sense here. At 1 and -1, this derivative is undefined. All that means is that at those points, arcsine and arc cosine have infinitely steep slopes, if you want to think of it that way. Or as you approach 1 and -1, the rate of change of y with respect to x becomes infinitely large or infinitely small, depending on what way you're approaching from. In any case, I hope that's a 1 minus x squared on these. On the arc secant and arc cosecant, you have x squared minus 1. Those are the reciprocals of sine and cosine, so they're the opposite setup. All right, now down to this last one here, y equals x to the e power. This is a variable raised to a number power. This is similar to like x squared or x cubed. It's kind of in between them. So it's a power function, and its derivative, dy over dx. I'm just choosing at random what to name my derivatives here. I have a new coefficient times x to 1 lower a power. And don't estimate as a decimal, just call it e minus 1. All right, so again, these questions are of there's 25 of them. That's going to be on your actual mastery test at 2 points each. There's 10 more questions, as I said, that are medium to difficult. They kind of start easier and get harder as we go on. And those are like the last 3 here. So I've got 3 kind of medium difficult, and yuck sort of difficulty level. So again, pause your video, maybe grab your derivative reference sheet if that's helpful, or see if you can do without. But I'm going to go over these now. The idea is look at the structure of this. This is a product. Ooh, let me just start this up. There we go. So I've got a product here, x squared times a tangent of x. So I'm going to use product rule. And my derivative then is going to be the derivative of the first factor times the original second factor, 2x times tangent of x. I'm just going to put parentheses around those for safekeeping, plus, all the way around, the original first factor times the derivative of the second factor. The derivative of tangent of x is secant squared of x. And we are done. So a little bit more challenging than what you see on the 2-point questions from the mastery test, but not too much. It's just we have 2 simple pieces in this one connected by multiplication. So on this number 7 here, maybe a little bit messier, but quotients are pretty easy to pick out. I've definitely got a quotient here. I'm going to need to use quotient rule, which involves finding the derivative of the numerator and denominator separately and putting together somewhat similar to product rule, just with a subtraction. And then it is a fraction overall, where this denominator is going to be squared in the denominator of our answer. So looking at the numerator and denominator here, neither one's too difficult on its own. I'm going to write this up here a little bit, though, because I know that question number 8 is going to take a little bit of room. But in terms of this, denominator is x squared minus 1 squared. Sometimes I write that first because, especially if it's a more complex quotient, it's easy to get distracted and forget to write out the quotient rule properly. It's easy to forget the denominator of it. I've seen that done many, many times by students accidentally. So derivative of the numerator, 5 is a constant, so that part's going to go away, but just 6 times natural log of x will be 6 times 1 over x. For the sake of space, I'm just going to write that as 6 over x times the original denominator, x squared minus 1, minus, other way around, the original 6 natural log of x times the derivative of the denominator, which also not too hard, just 2x. This minus 1 is a constant, so its derivative is 0. Or, like if this had been x minus 1, that's just that shifts the graph up and down. This would be the y-intercept on either a parabola or a linear function if it's just tagged onto the end like that on a polynomial. So just times 2x, and we're done. Now, this last one here, I left some extra space for it. A bit of a challenge, but kind of like the last problem we did on the first set of 5 problems today. Overall, I've got a square root function. So I'm going to do this one the other way around from how I've done some of the others, kind of work outside in. So to take a derivative of a square root function, if it's a square root of x, it's 1 over 2 root x. If it's a square root of something else, I'm going to go 1 over 2 times the square root of that something else, which is sine cubed of 6x minus 5 plus 9. Now, as a note, sine cubed of 6x minus 5, something that might make this easier to understand, notice this cubed here. We talked about this with a squared before. This means the same thing as sine of 6x minus 5, whole thing, to the third power. So it's a composition of functions, like 3 of them. So I've got a 6x minus 5 that I take a sine function of, and then I cube that result. So this on its own is a 3-part composition of functions. And it was also thrown under a square root sign. So there's a lot of levels to this. Just thinking about the construction of this, if you were substituting in a value of x, you could do the 6x minus 5 pretty quickly, just like you can take the derivative of 6x minus 5 pretty quickly. Then you have to take the sine value of that, and then cube it, and well, add 9, not very challenging, and then take a square root. So there's a lot of different steps to that. But thinking about this, well, I've dealt with the square root derivative. Now I've got to deal with what's under the square root, the inner function, which there's a plus 9, and I know the derivative of that's going to be 0, so I won't concern myself with that. Let's think about what's the derivative of this sine function raised to the third power. Well, something raised to the third power, when I take its derivative, is going to be to the second power afterward. And just like when you take the derivative of x cubed, you get 3x squared. If I have this sine function cubed, I get 3 times that sine function squared. Sine of 6x minus 5 squared. Now, so at this point I've dealt with the square root. I've dealt with the third power function. Now let's deal with the sine function, because we haven't taken the derivative of a sine function yet. Derivative of a sine function is a cosine function. Sine of x would just be cosine of x. Sine of something else has cosine of that something else. We're working our way in. So we've taken the trig derivative now, but we never did the derivative of this 6x minus 5. Well, that's just 6. It's a linear function. Power function, first power if you want. But you can see here we've got 1, 2, 3, 4 big chunks of factors. And I did these working from the outside in because there's so many levels to this. It might be hard to figure out where do I start. But if you wanted to think about this from the inside out, what do you do first with the x? Oh, you multiply by 6 and subtract 5. So this is the first portion. What's the derivative of that? 6. Then afterward, I find the sine value of that. How do I find the sine of something? Oh, well, I know how to find the derivative of a sine function. It's cosine, and then we worry about the cubed, and then we worried about the square root. This plus 9 and this minus 5, as we're going through, they just kind of get lost in the wayside when we're taking the derivative of that step, because they are constants which only shift things vertically if they'd been on their own. But overall, this whole long expression here is our derivative for number 8. And there's no need to try to simplify that or make it look pretty. Just make sure you have all the pieces there. Thank you, thank you.